Now we will solve a Hamiltonian format for the Klein-Gordon equation. The solution, we have seen that for Klein-Gordon equation there can be two different solutions corresponding to a positive energy and corresponding to a negative energy, or corresponding to positive charge density and negative charge density. So the Hilbert space associated with the Klein-Gordon system need to be incorporated with both these solutions that are independently occurring and are complete in their own regime also, that require a redefinition or an act of redefining the Hilbert space formalism for the Klein-Gordon system as well. Anyway, we will face it later on. The solution is now psi equal to psi plus psi minus column vector. For the sake of convenience, we represent it as psi 1, psi 2 column vector. Now psi 1 will be an average of psi. Of course, psi 2 also will have an average nature as long as the overall wave function psi is concerned. Then psi 1 can be written as half into psi plus psi. Mathematically it's true, it is 2 psi by 2, that is psi. However, we modify it in the sense that this is the solution corresponding to positive energy E plus, and this is the solution corresponding to negative energy. So half into psi is taken out, 1 plus E by mc square. E is the energy possessed by the particle. Mc square, of course, it is the relativistic energy. So E by mc square is 1. But I can incorporate right now E as positive energy EP, or energy having magnitude EP and psi plus. That is half into 1 plus. Energy E is positive, I have put the plus sign here. If it is negative, I might have put minus sign here. E is replaced by means of the operator IH cross dou by dou T by mc square is there, psi. And we keep it psi equation 1. Now psi 2 equal to half into psi plus psi again. It's an average of psi, overall wave function psi. That is half into 1. I have to incorporate this as negative energy minus E by mc square operating over psi. That is half into 1 minus E is IH cross dou by dou T by mc square operating over psi. Of course, psi 1 plus psi 2, upon adding these two, I will get psi. Psi 1 plus psi 2 equal to half into psi plus psi plus psi plus psi. That is half into 2 psi, which is psi. And subtracting these two equations, psi 1 minus psi 2 equal to half is common into 1 minus 1 vanishes. IH cross dou by dou T by mc square. That is IH cross by mc square into dou psi by dou T. Minus minus make it say plus dou psi by dou T. Or this is 2 dou psi by dou T, 2 vanishes. mc square is taken to the left side. mc square into psi 1 minus psi 2 equal to IH cross dou psi by dou T. Now, operating equation 1, this one, by IH cross dou by dou T, we obtain this IH cross dou psi 1 by dou T equal to, here this will be IH cross 1 by 2 is here. 1 by 2 I can put it outside itself. Anyway, I have taken it to the bracket for the first term. IH cross by 2 into dou psi by dou T plus IH cross by mc square into dou by dou T is there. It is to be operated by IH cross dou by dou T. So IH cross into IH cross minus H cross square by 2 mc square into dou square psi by dou T square. That is IH cross dou psi 1 by dou T equal to 1 by 2 into 1 by 2 is common into IH cross dou psi by dou T. This is the first term. And we substitute IH cross dou psi by dou T as mc square into psi 1 minus psi 2, because I have to incorporate psi 1 and psi 2 in this right side. mc square into psi 1 minus psi 2 minus H cross square, 2 is taken out, H cross square by mc square into dou square psi by dou T square. We have the Klein-Gordon equation del square psi minus 1 by c square dou square psi by dou T square equal to m square c square by h cross square psi. and I mean substitute minus 1 by c square dou square psi by dou t square here from plane Gordon equation. Minus 1 by c square dou square psi by dou t square equal to take del square psi to the right side, m square c square by h cross square minus del square psi. We substitute it here to make it IH cross dou psi 1 by dou t equal to half into mc square into psi 1 minus psi 2 minus 1 by c square dou square psi by dou t square is substituted. So I have plus sign here. H cross square by m is already here into m square c square by h cross square minus del square operating over psi. Here right now we replace psi by means of psi 1 plus psi 2. That's equal to half into mc square into psi 1 minus psi 2. H cross square vanishes upon opening this term. M also vanishes. What remains is mc square into psi 1 plus psi 2 minus h cross square by m into del square minus h cross square del square by m into psi 1 plus psi 2. That is IH cross dou psi 1 by dou t equal to mc square psi 1 minus h cross square by 2m del square into psi 1 plus psi 2. There are some identical terms, we omit them. mc square psi 1, mc square psi 1, 2mc square psi 1 minus mc square psi 2 and plus mc square psi 2 vanishes, minus h bar square by 2m del square into psi 1 plus psi 2. That is summed up here. mc square psi 1 minus h bar square by 2m del square psi 1 plus psi 2, or IH cross dou psi 1 by dou t equal to minus h bar square by 2m del square, which is nothing other than momentum square by 2m, b square by 2m, which is the kinetic energy, into psi 1 plus psi 2 plus mc square psi 1. Similarly, if you operate IH cross dou by dou t upon this equation, you can obtain an exactly identical equation for psi 2 as IH cross dou psi 2 by dou t equal to, these signs are altered here, not this one but this one and this one, h bar square by 2m del square into psi 1 plus psi 2 minus mc square psi 2. So these are the equation of motion satisfied by the two independent solutions of plane Gordon equation corresponding to positive charge density and negative charge density. We combine them in matrix form. IH cross dou by dou t operating over column vector psi 1 psi 2 equal to minus h bar square by 2m del square minus h bar square by 2m del square psi 1 psi 2. We open this, minus h bar square by 2m del square psi 1 plus minus h bar square, minus is here, minus h bar square by 2m del square psi 2 plus mc square psi 1 plus 0 psi 2. So mc square psi 1, this is the first equation, and IH cross dou psi 2 by dou t equal to h bar square by 2m del square psi 1 plus h bar square by 2m del square psi 2, which is h bar square by 2m del square into psi 1 plus psi 2 plus 0 psi 1 minus mc square psi 2, that is minus mc square psi 2. Now minus h bar square by 2m del square is taken out because that is p square by 2m. What remains here is 1, 1, here it is minus 1, minus 1 operating over psi 1, psi 2 plus mc square is taken out from this matrix, 1, 0, 0, minus 1, and you will identify this as say the third polyspin matrix, say sigma z. However, sigma matrices, polyspin matrices are defined in a space of spin, but we have seen that plane Gordon system are having spin 0, so we cannot call them as exactly polyspin matrices. These are matrices that are identical with polyspin matrices, and I will be labeling them with the symbol tau. So this is the third component of this operator matrix tau 3, mc square psi 1 psi 2, and this can be split up as 1 0 0 minus 1 plus I 0 minus I 0, and this is nothing other than tau 3 again, and this is identical with the sigma y, we label it say τ2. This is in fact, these matrices are defined in a space of charges. Charge, as you have seen or you might have seen it in particle physics, is the third component of isospin. So of course we can say that these matrices tau are defined in the space of isospin. Now this is τ3 plus I τ2 into minus h bar square by 2m del square is p square by 2m plus mc square constant 1 0 0 minus 1 again τ3. So we write it say IH cross dou by dou t operating over psi1 psi2 equal to τ3 plus I τ2 into p square by 2m plus mc square τ3 operating over psi1 psi2. Of course this is a matrix operator and this involves the different energy terms, so it is the Klein-Gordon Hamiltonian, and we represent the Klein-Gordon equation in Hamiltonian form as IH cross dou psi by dou t equal to hkg operating over psi1 psi2. Of course these matrices are second order matrices and then they corresponds to 2 degrees of freedom associated with the system, and these 2 degrees of freedom, as I have already told you, are defined, these matrices are defined in isospin space, and charge is the third component of isospin. This charge can have 2 different degrees of freedoms corresponding to positive charge and negative charge. So here the matrices τ3, τ2 and a possible τ1 having representation 0, 1, 1, 0 are defined in isospin space, and associated with this there can be 2 different degrees of freedom, and this corresponds to positive charge and negative charge. So this idea is also consistent with the Pauli and Weisskopf prediction. This also led to the success of the Klein-Gordon theory, though after a long expected duration. Now I have already told you the Klein-Gordon equation can have 2 different solutions, one corresponding to positive charge and the other one corresponding to negative charge, and these 2 solutions are independent and they themselves define 2 different parts for the Hilbert space associated with the Klein-Gordon system. But we already have a Hilbert space formalism associated with any quantum mechanical system with 2 different components for the wave function. One happens to be the dual of the other. They are related by means of a complex conjugation operation, and these vectors are vector in the prefactor space and the postfactor space, or the Ket space and the adjoint Ket space. Now we have to incorporate this idea with the occurrence of 2 different independent solutions in the same Hilbert space. This require or demand a redefinition for the scalar product of vectors, of course then for the nature of Hermitian operators, of course then a redefinition for the norm of the vectors, etc. We will now try this redefinition. For that, consider the charge density of Klein-Gordon system EH cross by 2 IMC square into psi star dou psi by dou t minus psi dou psi star by dou t. We have seen that IH cross dou psi by dou t equal to MC square into psi1 minus psi2. So we can take dou psi by dou t equal to MC square by IH cross into psi1 minus psi2. Take the complex conjugate of this equation, we obtain MC square into psi1 star minus psi2 star equal to minus IH cross dou psi star by dou t. We substitute dou psi by dou t and dou psi star by dou t in this equation. We obtain charge density rho equal to EH cross by 2 IMC square into psi star. Dou psi by dou t is MC square by IH cross into psi1 minus psi2 minus psi into dou psi star by dou t is MC square by minus IH cross into psi1 star minus psi2 star. Now we take MC square by IH cross outside, E by 2 MC square, H cross vanishes, I square minus 1 and this minus is put here. MC square is taken out, MC square will be vanishing in the next step. into psi star mc square vanishes. To make it say minus e by 2 into psi star, that is psi 1 star plus psi 2 star into psi 1 minus psi 2 plus psi 1 plus psi 2, that is psi into psi 1 star minus psi 2 star, that is psi 1 square, psi 1 star into psi 1 square, this one, psi 1 star into psi 2 with a minus psi 1 star psi 2, then psi 2 star psi 1 with plus psi 2 star into minus psi 2, that is minus psi 2 square, plus here also we open this bracket, psi 1 square minus psi 1 psi 2 star plus psi 2 psi 1 star minus psi 2 square. So all except psi 1 square and minus psi 2 square vanishes, and this occurs 2 times, psi 1 square plus psi 1 square minus psi 2 square minus psi 2 square, all the remaining 4 terms will be vanishing. As these are occurring twice, 2 is taken out and cancelled with 2 in the denominator. What remains is minus e into psi 1 star psi 1 minus psi 2 star psi 2. And that can be taken as equal to minus e into psi dagger. Psi dagger, as you know, psi is equal to column vector psi 1 psi 2 psi 1 psi 2, and psi dagger will be then equal to row vector psi 1 complex conjugate and psi 2 complex conjugate. Once you perform this psi dagger tau 3 psi, you will obtain exactly this one. And the equation of continuity necessitates that the total charge density a constant, integral rho d tau equal to a constant. For a single particle, total charge is either plus e or minus e. So integral rho d tau for a single particle can be taken as a plus or minus e. Now we replace rho by means of this expression we have already evaluated, integral minus e psi dagger tau 3 psi equal to plus or minus e vanishes. Integral psi dagger tau 3 psi d tau is equal to plus or minus 1. And this quantity that need to be plus or minus 1 happens to be the Paschen probability density. In Hilbert space formalism, it is nothing other than the square of the norm of the vector. So this must be the format of the square of the norm of the vector according to the Hilbert space associated with the Klein-Gordon system is concerned, and that we can obtain as a scalar product like this. Scalar product psi tau 3 psi. Now psi will be coming as psi dagger. Tau 3 psi is already there. That's equal to plus or minus 1. Then this necessitates this as the definition for the norm of a vector. The normal definition for norm of a vector is scalar product of the vector with itself, or square of the norm of the vector is scalar product of the vector with itself. And the modified definition need to be scalar product psi with tau 3 psi. In the post factor, the vector is to be multiplied by means of, pre-multiplied by means of, or operated by means of tau 3, the third component of the isospin matrix. Then that define or redefine the scalar product also. Scalar product psi phi is integral phi star psi d tau. You have to take the complex conjugate of the vector coming from the prefactor space as long as the normal definition is concerned. The modified definition, this happens to be scalar product phi tau 3 psi. That's equal to phi dagger instead of phi complex conjugate tau 3 psi d tau. Then the expectation value of the operator, in the normal definition this is scalar product phi a phi, and the modified definition you have to put tau 3 here, scalar product phi tau 3 a phi. A phi is a vector that is to be multiplied by means of tau 3 as a pre-multiplier. Then the definition of the Hermitian operator scalar product A phi phi equal to, let me send this operator from the prefactor space to the postfactor space. Then the operator is to be replaced by means of his conjugate cotranspose or dagger in the postfactor space. If this transformation is independent of daggering, then A dagger will be equal to A, and the scalar product will be scalar product phi A psi. There is no comma here. That necessitates this identification for the operator A dagger equal to A. Once this condition is satisfied, we say that A is a self-adjoint operator or a Hermitian operator. In the modified definition, already there is τ3 as a pre-multiplier in the postfactor space. And I intend to transform or send this operator A from prefactor space to postfactor space. Of course, it is to be replaced by means of its dagger. But for this to have the same meaning as that of this one, A dagger, of course it is equal to A, as A is Hermitian by its normal definition, should commute with τ3 here. Then only I can put τ3 as a prefactor here. So A dagger τ3 psi, of course it is equal to A τ3 psi, A τ3 psi, because A dagger equal to A. But that is not the demand for A to be Hermitian as long as the Klein-Gordon space is concerned. I must have to write τ3 as a prefactor, then only this is consistent with this one as per the modified definition. For that, this should be equal to phi τ3 A psi. This necessitates a modified definition for Hermitian operator A instead of A dagger equal to A, as long as the Klein-Gordon space is concerned. And this definition is A τ3. I must have the facility to write A dagger τ3, that is A τ3, as equal to τ3A. Once I can write this means that A τ3 equal to τ3A, A and τ3 are commuting or commutator A τ3 equal to 0. Then this will be the modified definition for a Hermitian operator in the Klein-Gordon space. All that operators, they commute with τ3, the third component of the isospin matrix, are Hermitian as long as the Klein-Gordon space is concerned. So this redefines the Hilbert space formalism and the vector algebra as long as the Klein-Gordon space is concerned. And keep in mind that the normal definition corresponds to positive definite normalization and real eigenvalues of Hermitian operators, whereas this modified definition necessitates both positive and negative normalization for state functions and both real as well as imaginary eigenvalues for the Hermitian operators. And with that we come to an end for the discussion of Klein-Gordon equation and the associated qualities of Klein-Gordon equation. I have already given you a note that has two supplementary questions. First one, the non-relativistic limit of Klein-Gordon equation. You can verify that this is nothing other than the Schrödinger's equation, and the Klein-Gordon equation can be written in terms of potentials. However, this cannot give you something new or any new concept, so we skip that ideas. You already have that mathematical formulation of non-relativistic limit of Klein-Gordon equation and the representation of the Klein-Gordon equation in terms of potentials. Now we move to the derivation and the associated success and discussion of Dirac theory.